Thank you. All right. So far we have mostly been discussing continuous symmetries. There are in many cases, or there are many ways, fundamental concepts, if you understand them well enough, it's not very hard to understand the discrete case. And as we saw already in examples, you can go from the continuous to the discrete by adding charged matter. So very often you can see it as a special case of the continuous case. But sometimes there's no very useful way to think about some given discrete symmetry in terms of the continuum, of a parent theory with a continuous symmetry. And in that case, you want to study theories with discrete symmetries directly. And that will require a little bit more technology than the technology I have introduced so far. So the first part of the lecture today will be about introducing the technology that I need, something known as simplicial cohomology. Now, you might wonder why we do this if we already have a perfectly good description of discrete symmetries. We can use symmetry generators. Everything I said so far about these topological operators works for symmetry generators. And we have a description of backgrounds. If you want to describe a background for a discrete symmetry, well, note first that discrete symmetries are flat. The backgrounds for discrete symmetries are flat. And by this, what I mean is the statement that they can be represented by networks. Of symmetry generators. And you can understand this, this phenomenon from the following observation. If you have some holonomy, and you compute the holonomy here, so the holonomy in this path, gamma, this belongs, so this is some G, this belongs to some, in this case, discrete group G, and if you take some small deformation of this path, because this group is discrete, there's no neighboring group elements, so the holonomy, so if it's gamma prime, the holonomy of gamma prime should still be G. That's simply because if you have a finite group, a discrete group, and if this is -1, it has to be -1 here also. So the curvature, in the language of differential forms, has to vanish. So here F is 0. So this is just a heuristic argument to motivate the fact that for discrete symmetries, you can, in principle, work always at the level of networks. Kind of networks I was describing. Now, in practice, I don't find this always useful when it comes to calculations. So I want to describe another way of talking about these things that, in practice, tends to be a little bit more useful. Sorry? No, this was a general thing. You compute holonomy around some cycle, and you get what you get. Okay. So for that, I'm going to introduce the ideas of simplicial cohomology, and well, first simplicial homology, and then simplicial cohomology. I know some of you know these things, but I think many of you don't. At least some of you don't. So just to put everyone on the same page, because after I go wild using this kind of technology, I'll introduce the basics. The two basic, so reminder, the most basic version of cohomology that probably most of you know. How many of you don't know the RAM cohomology? Don't. Okay. So you can construct a cohomology. Once you know differential forms, and differential forms we know, you can construct the RAM cohomology group. Assuming I spelled this correctly, of a manifold X, which is defined to be, yeah, I did spell it correctly. It's defined to be the forms which are closed, right? That's the kernel of D acting on P forms, divided by those that are exact. I can write that as the image of D acting on P minus 1 forms. So anytime we define a cohomology or homology, we'll have a similar kind of a structure. We'll have a differential operator, D, that squares to 0. And it moves in some complex, some sequence of spaces, like these omega p's, the forms of degree p. And we'll have some D that bumps us up or bumps us down, depending if we're talking about cohomology or homology. And to define the homology groups or cohomology groups, we'll take a quotient like this, closed modulo exact. It's always the same structure. The thing that changes is which kind of complex you have. What are the objects here that stand for gamma, and what's the meaning of D. So one version that's very useful is this definition for simplicial cohomology. Technically, okay, so one thing you'll realize very quickly if you start reading the math literature, there's a lot of cohomology theories suited for different purposes. So the one I'm describing here is a flavor of simplicial cohomology that Hatcher calls delta simplicial cohomology. Okay, I read Hatcher as if you all know who Hatcher is. It's like a family member for me. It has a really nice book on algebraic topology. Everything I'm going to say in the next little while is going to be from Hatcher. Simplified and distilled, but if you want to see more details, you can go to Hatcher. Okay, so what's a delta complex? So assume that we have a simplicial decomposition of some manifold, which I'm calling MD. That means that we take our manifold and we construct it by gluing simplices of d-dimensional simplices. The running example during this talk during this lecture, this is to keep something concrete in mind. I always find it helpful. It's going to be a torus. It's a familiar torus. And you can construct the torus by gluing simplices. What's the simplest way that I can do this? You can put a line here. Let me give it an orientation. The reason for the orientation will come clear in a second. But the thing that's clear is that these are simplices. So simplices in two-dimensional are just triangles. So I'm gluing two triangles in this way. This edge is glued to this edge is glued to this edge, and this edge is glued to this edge. Okay, so that's going to be my working example. All right. We need something more. So we choose some ordering of vertices for each simplex. All right. So notice that here I wrote a K simplex. So here k goes from 0 to d. So I'm including not only the top dimensional simplices, so these two big triangles, but also the one-dimensional simplices, so this line, this line, this line, and the zero-dimensional simplices, which is the point at the corners. Okay, so such an ordering of vertices for each k-simplex is known as an orientation. So again, going back to this picture, the standard simplex in 2 dimensions, something like this. It has 3 points, 1, 2, 3. As I map it into the torus in these 2 different ways, I want to label the vertices that come from here in a consistent way. I drew my arrows in such a way that I can read the orientation from these arrows, meaning that if this is 0, the label increases as I move with the arrow. So this is 0, then this is going to be 1, and then this is 2. This is the only assignment which is consistent for this simplex, which follows the direction of the arrows. Similarly here, if I call this 0, because there are 2 arrows going out, I can call this 1, and I can call this 2. Okay, so this is a choice of orientation, choosing the vertices in this way, the labeling of the vertices in this way. Of course, these orientations have to be consistent. So for example, I chose these orientations for the 2 simplex, and now this induces an orientation for the 1 simplex, which is consistent. This one is growing as the arrows go, this one is growing, and this one is growing. So delta complex this is a set of maps what you can call sigma alpha from some k-dimensional simplex to your target space. You can call in what? MD, I think. MD. And here I'm using the same concise notation that Hatcher uses. So here k, the dimension of the simplex, depends on alpha. Meaning I have some ways of embedding the top dimensional simplex, yes, but also some ways of embedding the one-dimensional simplex and some ways of embedding the zero-dimensional simplex. So I'm calling all these things sigma alpha. And I keep track of somehow the indices to know if I'm talking about a 0 simplex, 1 simplex, or 2 simplex. Okay, so it's a set of maps, but of course there's some conditions. And one of the most important conditions, if you want the full set of conditions, a couple of them are a bit technical, but this one is obviously necessary, is that subject to conditions. In particular, sigma alpha restricted to the faces of alpha, of sigma k, belongs to the delta complex. Okay. Maybe I should say what the face of a simplex is. The face of a k-simplex a face of a k-simplex is a k-1 simplex obtained by removing one vertex. So for example, in this 2 simplex, if I remove this vertex, I end up with the one simplex, which is generated by the other two vertices. If I remove this one, I end up with this one, and so on. So these are called the phases. If I have just the one simplex and I remove one point, then I end up with the other points. So a one simplex has two phases, which are 2 points. Okay, so all this is saying is that I have to glue things consistently, right? If I look at the phases of this particular simplex, the way I embed this phase has to be in the delta complex. It has to be on one of these maps. All right. Definition. The group CNMDA of, these are called N chains, is the free group generated by the sigma alpha of 4, sorry, I guess, plus u to MD. Okay, so this sounds a little bit fancy, but let's see what this is. I pick an N and I pick an A. A in this definition is some abelian group. It's possible to generalize this to other things, to rings and so on, modules, many things. I'm just going to stick with the simplest one, which is the one I need for the next few lectures. So A is some choice of abelian group. If you want to keep one group in mind, keep Z or Z2 or R. Those are good examples. Then you pick an N, a dimension, and then you look at those maps from N simplices, so this subset of all the maps you have here, those that send N simplices to M. So you focus on those that are of N dimensions. And then you take the free group over A. What does this mean? Notation. So these are formal combinations of coefficients I times the corresponding map. And these coefficients are in A. So very, very down to earth, what am I doing? If I'm looking at two simplices, I have, imagine you have a vector space where the basis elements are this simplex and this simplex, and a generic element of the vector space is obtained by taking combinations of these two simplices. So each simplex gives you one new vector in your basis. If I'm looking at one simplices, I have basis for 3 elements, and I have 3-dimensional basis space, and the coefficients in this vector space are in this abelian group. That's what it is. So schematically, we speak a multiplicity in A for each N simplex. Right? So let. Yeah, I'm coming to that, but yeah.
But I'm very confused about the fact that you're calling you're operating with your abelian group on a map from a simplex to analytical.
Yeah.
Not on the simplex itself.
Yeah. So there's technically this is based on delta complexes. I think the definition you have in your mind probably is the other definition for simplicial cohomology, which is you take a simplicial decomposition of this space, obeying some properties, and then you have a bunch of simplices, and you talk directly about those simplices. The problem is if you want that definition to behave properly, you need many more simplices. Instead of having two simplices for the torus, you end up needing, I think of the order of 8 or something, 10, I don't know. So this definition in terms of maps tends to be more economical for calculations, and is not more difficult in practice. Right? But I think what you have in mind is correct. It's just a different definition of simplicity cohomology. So you go to Hatcher, this is what he calls the delta complexes, which are, again, more economical. Yeah, no worries. Any other questions? All right. So let's compute, let's try to keep track of our definitions in this example. For the torus, C0 of T2 with coefficients in A. Let's see what this is. But at this point, it's probably good to label my complexes. Let's start with C2, perhaps. C2, and I'm going to call them L and U, I think. U and L. Let me call them U and L, these two simplices. So this group of chains is A plus A. Yes, two-dimensional vector space generated by these two elements with coefficients in A. C1 of T2 with coefficients in A. Okay. Maybe I can give them a name. I don't need a name for the calculation, but it helps me not to get lost. Call them A, B, and C. This is A, B, and C. And in this case, C1, well, I have three of these, so there's going to be A plus A plus A. And finally, C0. Well, I have just one vertex here. We call it V. So that's A. Okay, so far so good. Any questions? Sorry?
Could you please repeat how you calculated it?
Yes. So let's go back to the definition, right? Maybe the most transparent, at least to me, is that we pick a multiplicity in A for each map of dimension n. So I like to think of this as a vector space. For each n simplex, you get one basis vector. And they have coordinates in A. So I'm writing these vector spaces. Say that they have the points, for example. I have a single zero simplex, this V, a single one. Because I have a single point, I have one basis element. Coefficients are in A, so that's just A. If I have C1, C1 is three, I have, let's see, A, B, and C, 3 one simplices. I put A coefficients to each, and then I get A plus A plus A. If I wanted to keep track of things, I could call this A, B, and C, and so on. For the two simplices, I have U and L, and I get U squared.
Why do you have this single point?
Because this is a torus,
Oh, okay.
and so there's some identifications. Yeah. So, by the way, yeah, this is a good point. This is one of the reasons why the delta complex description is more economical than the standard description that came up before. Because in the standard description, you want these points to be different, and then you glue them at the end. So you need many more triangles. Okay. So in this example of the RAM, we basically have constructed these elements, the analog of omega. It will be our C's, the things in the complex will be the C's. We need a differential, something like the D. So it's going to be a boundary operator. So that's a definition. Boundary n of some sigma alpha. What is this? So it's the sum from I equal to 0 to n of -1 to the n. The map sigma alpha restricted to the corresponding phase. So that's the simplex generated by V0, Vi minus 1, Vi plus 1. Maybe, sorry, use this notation instead. Okay, so first of all, what do these brackets mean? The brackets mean simplex generated by these vertices. The hat means omit this vertex. So this is the phase associated with this vertex. I remove this vertex and I construct the rest of the simplex. I'm taking the map sigma and I'm restricting it to that. And then I'm putting some -1s that make everything else much nicer. So one exercise for you, standard exercise if you want to learn these things. Prove that if you take the boundary of a boundary, around, you get 0. Okay, so let's compute some boundaries. Let's compute delta 2 of u. This one here. Okay, and let's just follow the definition, right? This is going to be u, this embedding of these two simplex in my torus, first restricted to the one simplex that I obtained by removing 0, the phase associated to 0. So this is u restricted to 1, 2. Minus, yeah. Sorry, yes, thank you. Yeah, of course. Hi. Thank you. Okay. So, with the right sign, this is 0, 2, and then plus u 1, 2. No, let me see, 0, 1. That's the boundary of u. Now, this is written in abstract notation, but I have named my one simplices. So let's translate this into my names. U1, 2, well, that's V. U0, 2, that's C, very good. That's C. And U01, let's see if I get it, that's A. Okay, let's do the boundary of L. Similar, L restricted to 1, 2, minus L restricted to 0, 2, plus L restricted to 0, 1. See what I get? L1, 2, so that's A. L restricted to 0, 2, that's C. And L restricted to 0, 1, that's P. So it's actually the same as the boundary of U. Okay, let's do the others. Delta 0 on V, so the boundary of V, well, it's going to be 0. There's no -1 change, so this has to go to 0. And the next one, which is interesting, is the delta 1, the boundary 1, sorry, of any of these. So let's do A, for example. So it's going to be A restricted to 0 minus A restricted to 1. So it's V minus V, and that's 0. And you can easily convince yourself, once you notice this one, that this is the same for the others. So this is equal to boundary of B, and this is equal to the boundary of C. Okay, more definitions. N chains Cn such that so those that don't have a boundary are called N cycles. I'm pretty sure I've used this word many times during the lectures, so I assume you by now know what it is. I apologize, it's hard to resist. And the group of N cycles it's easy to prove that this is a group, I will meet the proof, is denoted Zn. Okay, so I can finally define simplicial homology. So the full name for what I'm going to write is a simplicial homology with coefficients in A, but of course that's very long, so I'll write something like this. Hn of Md with coefficients in A, and that's defined as the kernel of the d-dimensional boundary, so those things which are cycles, divided by the image of dm minus 1. So those things which are boundaries. Sometimes that's not a notation I particularly like, but some people like to introduce the notation Bn for boundaries. So those chains which are boundaries of a one dimension higher object, they call them Bn, and that's again a group. So you can, if you see the notation, now you know what it is. And this is, of course, +1, sorry.
So this way, the ratio, the quotient is between the Zn and the n.
Yeah, exactly, yeah. So that would be, okay. So then Bn, and these are boundaries. Yeah. Mm-hmm. Right, so let's go back to our example. And let's compute these homology groups. Okay, so from H0 of the torus with coefficients in A. Okay, so that's the kernel of T0 divided by the image of T1. Okay, let's try to understand this. I just showed for you before that every element in C0 is in the kernel because D0 is 0. So that's going to be C0 itself. And the image of D1, well, D1 vanishes. So this is 0. Now dividing by 0 is a good thing here. It means I'm not quotienting anything out. So this is just C0, which I computed before to be A. That's not too bad. Let's do just next. Yeah. Let's do H1. Again, this is the kernel of D1 divided by the image of D2. Okay, so what's the kernel of D1? Well, because D1 is identically 0, it's all of C1. And what's the image of D2? So it's constructed here. Is the subgroup generated by A plus B minus C. Okay, I'm using this notation in brackets to mean subgroup generated by. Okay. So what's C1 in this notation? That will be A, B, C. I have 3 generators, and I'm quotienting by this. Well, clearly, the subgroup generated by these 3 is the same as the subgroup generated by A, B, A plus B minus C. Right? Because you can generate these out of those 3, and vice versa. And now taking the quotient is trivial, and just killing this generator. So this is the subgroup generated by A and B. So it will be A plus A. Okay, so in the picture, what is that? We have an H0, which is the group of points modulo boundaries. We have a single point. In practice, what that means is that our space is connected. You can reach any point from any other point. That's what H0 means. H1 is the space of things that you can lasso around and you cannot unwrap. So if this is a torus, and I write it in a perhaps more visual way like this, I have a cycle here, which could be B, and a cycle here, which could be A, which is the same, I don't know, this one, which would be A. There you go. So I have these 2 cycles, and those 2 generate the H1 homology group of T2 with coefficients in A. And finally, H2. It's the kernel of V2 divided by the image of T3. So this is again the kernel of T2. Now how does D2 look like? Somewhere. So U and L generate the same element when I take the boundary. So this is going to be the subgroup generated by L minus U. If I take the boundary of anything of this type, I get 0, because boundary of L is equal to boundary of U. And if I add any other piece proportional to U, for example, it will be non-zero. So this is a abelian group, A. Yeah, so something I'm not going to attempt to prove. But you can look the details in Hatcher, is that these groups are independent of choices. So I made a choice of triangulation. I could easily have, for example, refined this triangulation in many ways. Then I could have start flipping faces. I could do many things. And Hatcher will show you that this result is independent of that. So it's a robust thing. Okay. And maybe if you want to have a bit of fun with this, so for the Klein bottle, show that, so I'm going to K, H0 of K with coefficients in Z is Z, so it has one component. H1 of the Klein bottle with coefficients in Z is Z plus Z2, and otherwise it vanishes. Hn bigger than 1 for the Klein bottle is 0. So I run out of space. Okay. Does everybody know what the Klein bottle is? Yeah.
Is there a relation between these simplified homologies and the fundamental groups of manifold?
Yeah.
Topological?
Yeah, the homotopy groups, right? Yeah, that goes under the name of the Hurewicz theorem, Hurewicz's theorem. So, how should I write this? Let me just write it in a corner. You can look it up in Hatcher. Probably the most useful thing in practice is that H1 of some space X, coefficients in Z, is the abelianization of pi 1. So this is pi 1 of X divided by everything in pi 1 that can be written as a commutator of things in pi 1. There's also a result about H2, and if your space is simple enough, this generalizes for things that are beyond H1. So if all your pi's vanish up to some degree, you have this one at that degree. Yeah.
What can I understand from each zero that my manifold is
Connected. Connected. Let's think about points. H0 has a very nice interpretation in that case. You have some manifold, right? It's a complicated thing. And you start with one point and some other point. These 2 points are the boundary. If the manifold is connected, they are the boundary of some gamma. So if this is A and this is B, the boundary of gamma is A minus B with some orientation. Probably, should I choose the, yeah. Yep.
So they are defined by the quotient.
Yeah, exactly. Now when you go to homology, when you go to H0, you identify anything that's a boundary with 0. So it implies that in homology, the class of A is the class of B. So any 2 points that can be connected by a path, they are the same element in homology. So what H0 is then counting is how many components, disconnected components your space has.
Because each couple of points that are connected are mapped into only one generator.
Exactly. 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 Because any 2 points in the same component, there's a path between them. That's what this is sometimes called path connectedness. And then imagine your space is the sum of these 2 spaces, which are disconnected. There's nothing connecting them. Then you have a point here, you cannot relate it to this point. But any other point in this space will be connected to this one.
So in this case, there is that plus.
Yeah, exactly. In this case, if I choose A to be set, this will be set plus set. Generalized set to the number of components. All right, so for those that don't know what the Klein bottle is this figure, this gluing, but inverting the direction of these arrows. So you construct a cylinder, but you glue it kind of inside out. So try to do the same exercise and see if you can reproduce those results. Right? So that was homology. Let's do cohomology. So an n cochain, I'm going to call it alpha in, sorry, maybe I should call it alpha. Well, yeah, I'm calling it alpha. It has nothing to do with the index for the maps, or it's a different alpha. In Cn from MD to A is a homomorphism from Cn MD with integral coefficients to A. Does anyone know what homomorphism is? It's basically a linear map. So just to get a bit of intuition for this, in physics, properly, we often write, if you get me some chain, Cn, we often write the integral over the chain of alpha. And what we mean by this is the evaluation of the homomorphism on sigma. So this is an element of A. So when I write actions, I'll write integrals of cochains over chains, and what it means is that you evaluate the cochain on that chain. It's a homomorphism, so this will produce the target of the homomorphism.
So for defining homology, of course, you use Z as
That's the useful choice. That's the useful choice, the kind of universal choice, yeah. If you just subgroups, you have fewer homomorphisms. That's the problem. It wouldn't make wrong, but this is more useful. Any other questions? All right. So this gives me the chain complex. I need a differential. So we define the differential. I call this kind of D. So this one goes up. In a way that makes a Stokes theorem work. So what does this mean? If I take the exterior differential of some alpha, and I evaluate in the image of some simplex, V0 up to Vn, plus 1, yes. Right? This is defined in the following way. I take the integral, removing the first one, so this is from V1 to Vn plus 1 of alpha minus the integral V0, V2 up to Vn plus 1 of alpha and so on. So I can write this a bit better perhaps as the sum from I equal to 1 to 0 to n plus 1 of minus 1 to the I alpha integrated over the corresponding phase. Now you will notice that these objects that I'm integrating over, the things I'm evaluating over, these are precisely my definition of the boundary, which apparently I erased. Yeah. Anyway, this was my definition of the boundary, if you check your notes. This combination of phases with signs. And because this is homomorphism, you guarantee that from here you can obtain So can you repeat that? Oh yeah, thank you. Yes. Yeah, so write this like this. You're right. So because alpha is a homomorphism, then we have that integral of the alpha over any sigma is integral over the boundary of sigma of alpha. So that's Stokes' theorem. Now, because we know, or I left it as an exercise, this is 0, we have, because of this property, that this differential also squares to 0. So definition, alpha in Cn such that derivative of alpha is 0 are known as cocycles. And the group is set N. By the way, I'm making a big deal of this, but maybe I should. The convention throughout the literature is that homology has indices down, cohomology has indices up. Okay, so you can recognize at a glance what you're talking about by looking if the index is up or down. Okay, and finally, I can define my cohomology groups, P, of MD with coefficients in A, as the kernel of D of the appropriate degree times the image of D. Now, at this point, we could try to unpack these definitions and do this for the torus example. Instead of doing that, let me use a property that already I mentioned in the lectures, which is Poincare duality. Actually, I'm not sure if I'm putting the accent right. Is it this way or this way? This way? The other way? This okay? Yeah, thank you. It's been a long day, so I know these things. So for orientable manifolds, MD, say. There's an isomorphism, which is often called Poincare duality. Poincare duality, which goes from H in homology, say, of MD with coefficients in A to HD minus N of MD with coefficients in A. This is an isomorphism, so you get to choose in which direction it goes. I find this definition a bit more intuitive for the following reason. You give me some element here, which will be the class of some chain. the image under this map would be the class of the delta function on the chain. So it kind of tends to localize you in the delta function. Of course, this definition makes much more sense if I'm talking about differential forms. But there's an analogous notion for discrete chains. You basically kill any part of the homomorphism that doesn't touch this chain. That's what it means. And there's the RAM isomorphism. That brings us back to the beginning. Let me do that later. Sorry, there's one more thing I want to say before that. So let me do that in a second. But there's one more thing I want to say about cohomology, which is that cohomology has a product structure. This is in practice very, very useful. So there is a product. It's not the cup product. That takes a couple of cochains of degree P and Q. And it gives me a cochain of degree P plus Q. Okay. Maybe let me be general. I was going to do this in 2 steps, but because I want to finish with this topic today, let me do the general definition from the beginning. So let me say that I have 2 P's and Q's, an MD, with groups A and B. MD B. So this is an operation that produces a cochain from MD to C. And this depends on a product. So I'm calling dot.
Sorry, why am
Huh?
the manifold of A plus Q?
Ah. No, yeah. Thank you. No, you're totally right. It does take a toll talking so much. Yeah, so this is a homomorphism between groups. So give me elements on A and B, I produce an element in C. So I have to know how to multiply things between A and B. Okay, so what's the definition of this? The simplest thing is I give you 2 elements, one from C and one CP and CQ. So let me call them elements phi and psi. So phi cup product with psi. So this one lives here and this one lives here. And I have to get something out of this that I can evaluate on P plus Q chains. So this acting on, let me use integral notation. On some chain, so let me do as I did before, V0 to Vp plus Q. Okay. Here I'm being a little bit schematic. I'm only giving you the action on one element in the basis, but of course these are linear, so you can extend. So what's this? The integral from V0 to Vp of phi, the product integral from Vp to Vp plus Q of psi. Okay, so this is the cup product. So a few notes. Often A and B are the same. And if they're the same, there's a natural product. These are abelian groups. So you can take the product in the abelian group. So that's one typical case. Another typical case is that A, or say B, is the Pontryagin dual of A, which by definition is the group of homomorphisms from A to U1. So because these are abelian groups, it's more natural to think of R mod Z, but this is just U1. So in this case, an element of A with an element in A dual is simply the evaluation of the homomorphism on A. So this is an element of R mod Z. So in writing actions, especially when we are doing gaugings, this kind of thing appears more or less all the time. Okay, more properties. If you take the coboundary, this operator D, with the cap product, behaves nicely. So this is the boundary of phi, cap product with psi, plus -1 to the degree of phi, phi cap product with the coboundary of psi. So this is as in the case of the RAM differential forms. One thing that's not as in the case of differential forms is that this product is not graded commutative on cochains. So, well, the inner formula is a little bit complicated, and I will have to introduce a little more structure. So let me assume that the two elements I'm multiplying, phi and psi, are closed. Then the cap product of phi with psi is -1 to the degree of phi times the degree of psi. The cap product with the opposite ordering. Oh, sorry. Psi. So this is what you will write for differential forms. But there's an extra term, which is a boundary. I'm not going to write it. It will require me to introduce a bit more technology. But it's something which is exact. So I don't have quite commutativity, and this makes some things a bit more complicated when dealing with cochains. But luckily, because that's an exact term, this implies that if you multiply the classes in cohomology, then you do have the graded commutativity. Okay. So now that I have a product, I can tell you that there are isomorphism in H. chloride. It tells me that H, the RAM of a space MD, is the same thing as degree P, is the same thing as the simplicial cohomology I just defined of degree P with coefficients in R. So I can think of these two objects as the same. And all the structures transport nicely. So if I write the RAM differential here, I write this one. If I write the wedge product here, I get the cup product. And if I write the, so I've written this, sorry. Here's the cup product and the integral behave nicely. Notice that integral means different things on both sides. Here's the integral of forms, here's the evaluation of homomorphisms. Okay? But these definitions are compatible. Once I construct an isomorphism, I start taking cup products and integrals, everything behaves consistently. Okay, so that's all I wanted to say about homology and cohomology. If you want more details, you can ask me, or alternatively, you can spend some nice evening with Hatcher, and he explains all these things. Yeah.
What you wrote there, 5 cut side, no, on the other blackboard, that's there, that formula, where you decompose it.
Yeah.
What happens if, for example, there's a link in between cycles, like on the torus? Can it always be decomposed like that? Or could there be a case if there's
Right. So here I'm defining the action on the basic simplex. I just pick an ordering for the vertices and I define the product in this way.
How can we be sure it doesn't depend on, like, if we choose different decomposition, is that independent?
Oh, the different decomposition here. Yeah, no, it will depend. So part of the complication that I didn't write there keeps track of these choices. Indeed, the thing that's independent of choices at the end is the cup product in cohomology. But yeah, you have to take quotients to get rid of these dependents. There's some arbitrary choices. In this language, it will be the arbitrary choice of the ordering of my vertices. I have a P plus Q simplex. There's no canonical ordering of vertices. I do that as I want. So this splitting is more or less totally arbitrary. Yeah, indeed. Yeah.
I'm sorry, why do we want PNC to be closed?
Well, no, you don't have to. There's a definition of the cup product for any cochains. But the thing is that if these are not closed, the thing that you get here is not exact. And I didn't write it because it will force me to define a different version of the cup product called cup1, which requires a few minutes to discuss. And it's not very important for us at the moment. Yeah. So it just simplifies the formula that I'm writing. Right. So the whole point of this exercise was to be able to talk about discrete backgrounds in a systematic way. Now we have the technology. So let me go through some of the most important examples. Well, one of the most important examples, perhaps, which is n equal to 4 super Young Mills. Okay. This is a theory that has discrete one-form symmetries. So there's n equal to 4, d equal to 4, gauge algebra SU2, super Young Mills. So thanks to Ali's lectures, I assumed you know everything about this theory, but I'll review it slightly. One thing that we know is that I wrote an algebra here. So the choice of algebra fully fixes the action. So am I right in thinking that Eli has explained the Lagrangian of this theory to you? Yeah. And the only data you needed for that action is the algebra of the group. All the fields in equal to 4 are in that joint. So that means that you only care about the algebra. But as I will explain in a minute, the n equal to 4-dimensional theories depend actually on the group, not just the algebra. So the data is hidden somewhere that's not in the Lagrangian. And for that, let me start by discussing the difference purely in field theory, purely in group theoretical terms, between two objects with the same algebra, SU2 and SO3. So both have G equal to little SU2. My conventions is that small means algebra, big means group. So they have the same algebra, but they differ in the representation theory. So the irreps of SG2, the reducible representations of SG2, are labeled by half-integral spins. So that's just fancy notation for 1/2, 1, 3/2, 2, and so on. But the irreps of SO3, they are labeled by, I should write the 0, right? This is the singlet. These are labeled by integer spins, and so on. This is familiar to everybody, I expect. So I'm going to refer to this label as the spin. I emphasize that I can have fermions or bosons with these labels. Here I'm only talking about the spin under the gauge group, right? I'm not talking ever in the next rest of the lecture about a spin in space-time. When I say spin, I just mean the representation under SU2. So this is probably very familiar to most of you. Something that's probably less familiar is that there's a translation of this to the language of bundles. Okay, so there's two kinds of bundles. There are SU2 bundles, these are bundles that can be coupled to dynamical matter in any representation. I will explain the distinction in a second. And you also have SO3 bundles. Where we only require that irreps of integral spin can couple. Okay, so what does this mean in practice? Let me first emphasize that there are going to be more SO3 bundles than SU2 bundles. Here we're imposing fewer conditions than in here, so this group is bigger. There are more bundles of this type. But what does this mean topologically? Imagine that you have an S2, and you want to define a bundle of this type, which is locally of SU2 type, or SO3 type. Well, if you want to understand bundles in the sphere has a nice decomposition into open sets. You have the northern hemisphere and the southern hemisphere, right? And they are glued across the equator. So if you want to give me a bundle, the topology of the bundle is encoded in the gluing function on the equator. So what's this? This is a function, G, going from S1 to my group. Right? I have two bundles. Locally, they are both SU2 or SO3. I go from this patch to this patch by a gauge transformation, which is a gauge transformation. At each point in my spacetime, it gives me an element of the gauge group. Now, I have slightly thickened for the picture the overlap of the two patches. It's a cylinder, but this is, of course, contractible to the S1. So the topological information is going to live in the S1, just an S1. So up to the formations, the class of such maps is going to be given by pi1 of G. The class of the formations of maps between S1 and G is pi1 of G by definition. So let's see which kind of bundles we can construct with SU2 structure and with SO3 structure. Right. And this came up already in some lecture before, I think. Recall, if you know this, and if don't, just believe me, that SU2 is homotopic to the 3 sphere. And SO3 can also be written as SU2 mod set 2, where the set 2 is the center. So in this group is a matrix U, which is simply -1, 0, 0, -1. So in terms of the sphere, what this is doing is identifying opposite points in the sphere. You have the 3 sphere, and you identify antipodal points. So this sometimes has the name RP3. Okay, so let's see which kind of bundles we can put of each type on the geosphere. Pi1 of S3, just 0. If you try to lasso the S1 and 3 sphere, it can always collapse. But this one is not 0. I can't remember. I know I did this in somewhere this week, but was it a lecture or was it a Q&A session? It was a Q&A. Okay, let me repeat the argument then for those that were not in the Q&A. I'm going to argue that this group here is non-zero, and in fact is set 2. And the idea is as follows. I'm identifying antipodal points. So I have an identification like this. And I want to define some map from S1 that I cannot wind down. They cannot collapse. So here's an S1. I start here, and I go around the sphere to the antipodal point. Because there's a quotient, now these two boundaries are identified, so this thing doesn't have a boundary. It's a bit like the edges on the torus, right? We have two boundaries, but they're glued together, so they disappear when I take the boundary. So this is a map to DS1 that I cannot shrink down, because these 2 points are always antipodal points. No matter what I try to do, they're kind of frozen there at antipodal points. But now if I take 2 of these, well, then what happens? I can, let me give them an orientation just to make the picture a bit clearer. I can sort of take one of them and move it around the sphere to the opposite side to get a picture that looks like this, the original point. It came this way, and then it continued this way. So now, of course, this is unwindable, contractible. So this maps to the identity map on the sphere. So mapping the whole S1 to a point, and that's 0. So yeah, this is a set 2. If I take 1, it's fine. If I take 2, I can contract it. So we learned that there's no non-trivial SU2 bundles. Everything is topologically trivial. But there's a set 2 of non-triviality in SO3 bundles. In practice, what does this mean? If I have a map of this type, one of the non-trivial types, I'm taking a circle in the group. So this is the group here. I'm taking a circle from the identity in the group to the center element. So this is 1, 0, 0, 1 to -1, 0, 0, -1. As I go around the equator in my actual physical S2, I go from 1 to -1. In SO3, that's fine. That's a fine gauge transformation. But in SU2, it's not. Gauge transformations have to be a map from the space to the group. It cannot have any ambiguity. It has to close. So if this element of SU2 acts trivially on the dynamical particles, then I can couple it to an SO3 bundle of this type, even if it's -1. So particles of integral spin are not acted upon by the -1, -1. Here's a quick proof. If I take the fundamental of SU2, and I take the tensor product with the fundamental of SU2, I get a singlet and a joint. So you can generate any representation of integral spin in this way. The singlet clearly is acted trivially by the -1, and the adjoint is acted twice by the -1, so it acts as the identity. So anything of integer spin is not acted upon by the -1, and it can couple to one of these bundles. So why am I saying all this? Because in n equal to 4, all my dynamical stuff is in the joint, or more generally in representations of integral spin. So I can choose if I couple my theory to SO3 bundles or to SU2 bundles. Okay, so more generally, on some four manifold M4, the obstruction to couple half integral states or particles to my bundle is measured by the Stiffer-Whitney class known as W2 of my bundle So E is the name of my bundle. And this is an object that lives in cohomology of M4 with set 2 coefficients. I cannot explain this in a lot of detail. Just believe me that there's a class that you can construct that measures that. But hopefully the intuition is clear. Remember that the objects in this H2 are cochains. These are homomorphisms from 2 cycles to set 2. So basically it's telling me, give me any 2 cycle, and I will give you a sign, a 0 or a 1. So the computation that the Stifler-Whitney class is doing is this kind of computation. It's looking at the 2 cycle, and it's seeing if the transition function is an element that glues properly in SU2, or it only glues properly in SO3. Yep. If you want to see the definition more in detail, a good book is Botan 2, for example. I think so. Okay, well, ask me for references if you want references. I think Botan 2 is good, but there may be others. Okay.
Can you repeat that part? How can I measure the obstruction?
So treat this for the moment as a black box. If I give you a bundle, there's an object that you can construct, the Stifler-Whitney class, that lives in this group and that measures that obstruction. Actually, computing the Stifler-Whitney class requires you to know something more about the bundle. So very often, if you construct a bundle by gluing simpler bundles, there are formulas that allow you to compute the W2 of that bundle from the formulas of the constituents, for example. That's a standard technique. For what I'm going to say today, thinking of this as a black box will be enough. Okay, so now I can define the difference between SU2 and SO3 as n equal to 4 theories. So definition. Let me just write the partition function. If I write the partition function of SU2 on some 4 manifold, some coupling parameter tau, this is defined to be the sum over those bundles that have 0 Stifler-Whitney class, so those that potentially allow for dynamical particles in half-spin representations, of the path integral of A and the other fields. So A is a connection on E. And now the exponential of minus the action of n equal to 4, which depends on tau and A and the other fields. I don't need to be very explicit for what I want to say. This is the action that Eli wrote at some point in the lectures. Of course, you have fermions and scalars. I'm not writing them, again, because they don't matter for my arguments. And then you have the partition function of the SO3 plus theory. I will explain the plus in a second. Well, let me just write plus and minus. On M4, tau. So in fact, there are 2 variants of the SO3 theory that we call plus and minus. And the partition function is defined the following way. Now is the sum over all bundles. I don't impose the condition that the second Stifler-Whitney class is 0. I do the path integral over connections. The same n equal to 4 action. But then there's an extra factor, which is plus or minus 1, depending on the variant of the theory here, to the Pontryagin square of W2 over 2. So I have to define what the Pontryagin square is. So the Pontryagin square, in general, it's an operation from H P of some manifold with coefficients in Z2 to H P to P of some manifold with coefficients in Z4. It can be defined more generally beyond 2 and so on. Some of you might know this, but let me do this simple example. So in simple cases, in my case, this is an operation from H2 to H4 of a 4 manifold. So this is something I can integrate over the whole manifold, and sorry, I should have. So this is the integral over M4. So this is now a number which is Z4 valued. I divide it by 2, and I lift plus or minus 1 to that. Now, so whenever M4 is spin and torsion free, that means that there's no torsional subgroup of H2. Then I can define the Pontryagin in a simple way. Pontryagin of X is X bar square mod 4, where X bar belongs to H2 of M4 with coefficients in Z, and X bar is equal to X mod 2. Okay, so this was a lot to digest, I'm aware. But that's all to say that you can think of this Pontryagin square of W2 as W2 square. There are some topological subtleties in some cases, but in general, you can think of it as a standard square. Yeah. You want to switch the order here? Well, yes. I'm reading this thing as these two things agree when both are reduced mod 2. One of them is trivially reduced mod 2. Yeah. Yeah. Okay. And another property is that when M4 is spin, the integral of X bar square mod 2 is equal to 0. So for spin manifolds, if you integrate two form squared, you always get an even class. That means that this object that I'm introducing here, in kind of standard cases, is always plus or minus 1. Because this thing is even, and it's plus or minus 1 to an even number.
Sorry, so if it's not spin, it could be odd. So how is the Pontryagin square over 2 defined?
Well, this is, if you define it as exponential of pi I times the Pontryagin square, if you want. Pi I over 2.
But so if the manifold isn't spin, the Pontryagin could be...
Yeah, they can be. So this is on phase in general. Right?
Okay.
Yeah.
So, I mean, like the square root of minus 1 is already
Yeah. Okay. I was being a bit lazy. Replace minus 1 with the exponential of pi I.
Oh, okay.
Yeah, and then it makes sense. Yeah. Okay. Yeah. No, that's a great question. So this works equally well for n equal to 0. Yeah. Some of the things I'm going to say next are only valid for n equal to 4. But yeah, at this level, that's true. Okay, so notice that I haven't pushed a restriction on the sum over bundles. And at this point, it's a natural question to think if any of this restriction is inconsistent, or if there's a natural choice or anything like that. So what we will see is that there is no natural choice because these two things are related by duality. They're secretly the same theory. So there's no privileged choice in here. I have to live with both. Okay, so that's the statement of Montone-Olive duality. Or sometimes SL2C duality. And it's the following statement. If I compute the partition function of the SU2 theory, well, let me make it more general. The statement is that n equal to 4 with gauge group G and coupling tau is equal, up to some slight subtleties that we'll discuss, to n equal to 4 with gauge group the Langlands dual of G and coupling minus 1 over tau. So this is known as the Langlands dual, or GNO dual sometimes. So let me give you some examples. You take G, the Langlands dual here, Langlands dual. For example, for U1, with the standard quantization, is U1 again. So U1 we say is self-dual. That's something that I actually proved during the lectures, right? Sorry? I'm really sorry, I cannot hear.
When you write Langlands,
Mhm.
you mean the Langlands program?
Yeah, this is related to the Langlands program. I'm not going to pretend that I understand anything, but this is the name that is given out for this. Yeah. Sometimes in physics, this is also called the GNO dual for Goddard, Nuits, and Olive. It has different names. Okay, for SU2, the claim is that the dual is SO3 plus. For SO3 minus, the claim is that the dual is SO3 minus. Let me do a few more. For SUN, the claim is that this is PSUN, so SUN quotiented by the center. So this is a special case of that. I should put some pluses and minuses. So if you want to see details of the extra decoration that I need, this is in a really nice paper by Haroni, Cyber, and Tachikawa. Okay, so there's some extra decoration similar to these plus and minuses that I should include. Maybe one more, which is interesting because these have all the same algebra, so you might think these are just details. But there are cases in which you have different algebras. So for example, you have the USP2N group. The dual is SO2N plus 1. If you're not familiar with the notation USP, what I mean is the SP group, where USP2N is SU2N, where SP2 is SU2.
Sorry, and can we see this from the Dinkin diagrams, for example? Is this related?
It's related, yeah.
if you change like the colours of the different diagrams?
It can be read from the thinking diagram, but the operation is not entirely obvious. You have, in this case, that are non-simply laced.
Yeah, we have two different colours, like black and white.
Oh,
If you change the colour to be half from one group to the other.
I don't know. Yeah. I'll have to do it. I don't remember off the top of my head the coloring for USB and so. Maybe you're right. Okay, so maybe given the time, I'm just going to tell you a little bit about the evidence for this, and then next time I will discuss the symmetries, the set two symmetries. All right, so one piece of evidence, a very convincing one, is in a paper by Buffa and Witten. That's the reference somewhere. TH. Where they show that, well, among other things, not the only thing they show, but you take the partition function of SU2 on K3 with coupling tau. This is equal up to some factors that don't matter too much. And for this discussion, the partition function of SO3 plus of K3 with minus 1 over tau. So they actually go and they do the computation for n equal to 4. N equal to 4 is simple enough that you can compute the action explicitly in K3, a very special 4 manifold. And they find that these two things agree as predicted by that. Now, remember that our distinction between these two theories depended on having two cycles in there. So you need a manifold which is interesting enough, and K3 is certainly interesting enough. So I highly recommend the paper. They have beautiful analysis where they show these two things are the same. At the time, they weren't. They didn't have this language of plus and minus, but the calculation they do is this one. They don't include the extra factors here. You can, if you want to do a little exercise, take the ideas in Buffa and Witten and show that the partition functions in the SO3 minus case are self-dual. So let's finish here, and next time I'll say something about the discrete symmetries in the n equal to 4 theory.